from our very own Jadavpur University. So, sir, we are very much interested and we are patiently waiting to hear from you. Over to you,
Okay,
sir.
thank you so much. So let's start. So the title of the presentation, as you can see, is Brain-Computer Interface for Neuro-motor Rehabilitative Robotics. Now, we had a long desire actually to have, an intricate circuit, an IC, to be placed inside the brain so that this can control the this can be used as neuromotor rehabilitative device. That means people know who has lost their arms by accident or otherwise, but they had their arms, normal arms during their birth time. But after some time, because of accident or because of wounds, they have lost their arms. The question is, can we rehabilitate those people with artificial limbs by a robotic arm or any other arm as possible? And can we control their brain by some device placed in the brain, as you see here by a device? This is due to Elon Musk. As you know, Elon Musk has designed one such for one patient, he at least could recover some of the neuromotor disabilities by placing one integrated circuit inside our brain, inside his brain. So we are having the same kind of research, but we did not achieve so much until this time. Right now, we could control the motion of an artificial robotic arm by human thoughts. So I'll be demonstrating in the presentation how a person who has lost his arm can control a mobile robot, automatically just by his thought, so that he can bring a cup of tea forward towards his mouth, so that he'll be happy to have a cup of tea, automatically transferred from the table to the person's mouth by a artificial robotic arm. And this is called neuromotor rehabilitation. So what is brain-computer interfacing? As you see, in brain-computer interface, we must have a computer and a human brain. But the computer generates certain stimuli for the brain. The stimuli could be visual, or audio, or tactile, or aromatic. And the brain, on receiving the stimulus, generates some responses. The responses are electrical signals or images from the brain. Those signals or images which are response to the audiovisual stimuli or tactile stimuli goes to the computer. And the computer then tries to understand the interconnections between the stimuli generated and the actions responded by the brain in terms of signals or images. So is there any kind of correlations between the stimuli generated and actions? That is the fundamental thing the computer has to identify. In case it can identify, then it has a lot many benefits. What are the benefits? For example, you try to make the brain doing something as you wish. You can generate the corresponding stimuli because you know the stimuli and the action pair. So if you want to get the right action by the brain, you'll be generating the corresponding stimuli from the computer. So this is most useful to have a stimuli action pair, identifying the stimuli action pair, by such BCI arrangement, so that you can make the brain do something that you really wanted to do by generating appropriate stimuli. Now there is one point that is, brain, what is then BCI? BCI means a non-muscular or artificial channel of communication between a human brain and a computer. Okay. So this is very, very useful. You do not use any standard muscles or nerve fibers. You are generating the stimulus, generating the stimulus from the computer and actuate the signal, get the signal out from the brain's scalp, in our case, scalp of the brain, so that electrical signals only right now, but we have functional near infrared spectroscopic images where you can image also from the brain and convert that image into signals. But right now we are considering only signals or EEG-based brain-computer interface, where by getting stimulus, the person will liberate some electrical signals which will be actually acquired from his scalp by placing a number of electrodes on the scalp. Now the question is, how does brain liberate electrical signal? When the person observes some stimuli, say visual stimuli, for example, there is a screen or a computer screen or a blackboard screen, whatever it is, where there is certain stimulus, and the person observes the stimulus. As the person observes some stimulus, he will be reacting to this, and his reaction appears as a number of I mean, positive and negative charge pairs. They are called dipoles. Dipoles means positive and negative charge pairs of equal magnitude but a small gap between them. They are called dipoles. As you find, there is a small gap. A large number of such dipoles is created in the brain at a particular region which is actually processing the stimuli. For example, if you see a certain particular kind of, say, stimulus, for example, say a rising sun on a screen, then some portion of the brain, particularly in the occipital lobe, somewhat here, will be actually actuated. And that part of the brain will be liberating some signals. Whenever, suppose you find on a rooftop, a person, child is playing, and there is no boundary of the rooftop, and her mother and, say, grandmother, they are talking inside the roof, but the child is very close to the edge of the building, and the child might fall at any time, and you are at a far distance. Even if you shout, the mother and grandmother cannot see. You are at a far distance. You can watch the child that he is just at the edge of the top of the building, and he might fall at any time. So as you observe the scene, and you are helpless, because you cannot, even if you shout, you cannot help the mother and grandmother. So what you can do? Simply at that time, your brain will be liberating some signal, a fear stimuli. It will be fearful stimuli you will be generating, and then your some part of the brain, I mean, will be liberating some signal, that is P300 signal from the parietal lobe, somewhat here. So it will be generating. So our brain liberates certain electrical signal because the dipole concentration there will be more whenever we do certain, we can see or we can feel certain stimulus. Okay, it need not be always visual stimulus, it can be audio stimulus. Suppose someone is actually, over telephone. I mean, he is saying, unfortunately, he is saying rough words in telephones. You do not know the person. Suddenly, he took up the telephone and started abusing you for no reason. Initially, you are fumbling. What happens? You do not know the person. Why is saying like this? So your brain will be actually anxious at the time, and you will be liberating some signals from the prefrontal lobe as well as parietal lobe. So the question is, we are liberating signals from part of the brain which are active at that time point, depending on the type of the signals which are appearing, which could be visual, could be audio, could be touch signal, like this. One of our students, I mean, right now she is a professor of, IEM, Kolkata, in Artificial Intelligence Department. So, Mousumi Daha, actually. So, she did an interesting experiment to actually identify when a person, maybe his father or mother, her father or mother, or maybe her child, or say her say husband, whenever any one of them touches the palm and she is blindfolded, can she recognize the person? And when she can recognize the person, can any distinct information is obtained from the brain of Moshami? The answer is yes. I mean, we have found different kind of brain signals from the different regions of the brain when her child touches her at the palm, on when her husband touches her at the palm, on when her mother touches her at the palm. We are getting different signals. That means she can discriminate them, and automatically, even she are blindfolded, and the brain can recognize it by producing different signals. So you understand, so because of, such, dipoles, the potential at any point on the scalp, that will vary. If the dipole concentration vary, then potential will vary with time. And as the potential varies with time, we are getting some electric field, or as well as voltage waveform over time at any point on the scalp. So an EEG acquisition device actually collects those signals. These are electrodes connected on the skull, and the EEG acquisition device is developed actually to get those signals from the skull, okay, and then amplify those signals and convert this. So it is amplifying those signals, and then there is a low pass filter, hardwired low pass filter, to convert, to actually filter the signal between 0.1 hertz to 100 hertz and attenuate the rest of the signal, because most of the EEG signals are confined to 0.1 hertz to 100 hertz. So if you have a low pass filter with the upper cut of 100 hertz is good enough, and we can get the signals from different channels, CH1, CH2, CH3, the similar signals are obtained in the way. So in an EEG machine, we are acquiring the signals from the skull, amplify those signals by multiplying by a factor of 60 to 100, and having a low pass filter by getting the signal with a cutoff frequency of 100 hertz from different channels as we find. After we get the acquired signal here, we need to add on the orange marked blocks. What are the orange marked blocks? Excluding the person. Person also looks orange here, unfortunately. But the orange marked black blocks are band pass filtering. Then for individual cognitive tasks, we have to filter the signal in the respective bands. For example, someone is sleeping. To identify the sleep kind of activity, for deep sleep or mild sleep, all those kind of thing you can determine, and you have to then determine at a certain frequency band, at very low frequency, 0.3 hertz to say 2 hertz, like this. Whenever a person is, I mean, say, praying before God, so she will have a different frequency range. Whenever a person is swimming, he will be having a different frequency range. So at every cognitive task, the frequency range will vary, and therefore you need to use specific band pass filter of desired frequency band. So in our motor cognitive task, whenever a person has to liberate motor signal to activate a motor, we have to see the signal from 2 to 18 hertz. So the band pass filter has the frequency band, I mean active frequency band from 2 to 18 hertz. Then from the signals, bandpass filtered signals, which is basically a digital filter. Up to these yellow blocks, basically they are all active, they are all, I mean, say, a passive device, passive components. So it is LR filter or hardware components. But this is basically a digital filter or a program, basically. It's a program. And then by the digital filter program, we are getting the filtered signal between 2 to 18 hertz for motor control signals. And we extract certain features from the signal, feed it to a classifier. The classifier will classify it, what is our intention. If my intention is to move my left hand or right hand, or no, nothing to do with left or right hand, it will have three classes. The classes say whether I wanted to move my left hand, one output will be high, other will be low. When I want to move my right hand, the second will be high, other will be low. When I want to do nothing, the third will be high and the other two will be low. So depending on that, we can classify the brain signal from based on certain features. And then sometimes we can feed it to a robot arm or a controller. So the signals, suppose based on the signal, signal amplitude, or based on the signals generation, we can feed it to a robot to do the necessary task. So this is an actuator or a manipulator connected with the control signal to do the necessary task for the robot. So scope of the research here is on signal processing, like filtering and feature extraction part. So first is signal processing, second is feature extraction, third is classifier design, and lastly the robot controller design. These are scope of research for the present problem. Now I say a few brain signals. The first signal is motor imagery signal. Suppose during time interval from here to here, you are thinking of moving your right arm. As you think of moving your right arm, or you are really moving your right arm, you will be liberating same signal from the motor cortex region somewhat here in the brain. The left side signals, I mean C3, they are basically representing right half of your brain, right half of your right hand or right leg. The right half of your brain represents the left leg or left hand. So basically, the C3 signal basically corresponds to your right hand movement, and C4 signal corresponds to left hand movement from the motor cortex region. So when the person thinks of moving his any hand, effectively the signal amplitude, I mean, suppose the person is thinking to move his hand between this time point to here. So the signal amplitude, which are a value initially fluctuating around some equilibrium value, now started decreasing as the person has started thinking of moving his hand. So the signal amplitude decreases. And once he stopped thinking, the signal amplitude will gradually grow and then becomes equal to the original signal amplitude it had few seconds before. So this signal, when the signal amplitude is falling, is called event-related desynchronization or ERD. And when the signal amplitude is increasing, it is called event-related synchronization, where the synchronization in the sense the power output here will be matching with the original power output before the V type of curve started. So this is called synchronization signal. So this part is called ERD and this part is called ERS. The together thing is called motor imagery signal. So motor imagery is a V type of signal. The other important signal is error-related potential, ERRP. Error, ER for error, R is related, and P means potential. So basically, we are getting error-related signal from the midline of our brain. And anywhere on the red line, as you find, anywhere you place electrode, we'll be getting the signal. But it has best response in the parietal lobe somewhat here, called the PZ electrode. So ERRP actually looks like this. Basically, whenever you find somebody doing any mistake, or you can recognize that you did mistake, somebody could be a person, could be a robot, or anything. Whenever that person or a robot makes any mistake or commits any mistake, and you can realize that they committed mistake, automatically it will be liberating a signal like ERRP signal, which first becomes negative, then positive small, and again have a small negative value. These three cycle value, negative large, positive small, and negative small, again is the signature of the ERRP signal. Using these two signals, we'll be developing some protocol for motor control. Now suppose there is a, as you can see, there is a structure on a ellipse-shaped structure. Green colored pad is an ellipse-shaped structure, and this is the beginning of a pointer which is connected to a motor. So motor is connected with the pointer in a manner such that motor axis is perpendicular to the plane of the screen. So motor is perpendicular to the screen, and motor axis is actually connected with the deflector, as you find here. So the deflector is initially at the start point. As the person thinks of moving his right hand, the deflector will start moving clockwise. As it moves clockwise, it at any point of time, it will cross the stop point. And once it attempts to cross the stop point, the person will be liberating the error-related potential signal. And by that signal, because error-related potential signal will be liberated because the person finds the robot arm, crossing the target point or stop point, but the robot arm is supposed to stop there, that he knows. So when it crosses the stop point, the person is liberating an error-related potential signal anywhere from the midline of his brain and mostly in the parietal lobe, so piezoelectrode electrode. So this is the motivation. That means the person will think of his arm, then he will be liberating the motor imagery signal, that is the motor imagery signal. And by that time, the motor robot will be on, robot becomes on after motor imagery signal. When the robot attempts to cross the stop point, the person will liberate the ERRP signal. And by the ERRP signal, we can make the robot off. So robot is made off. But by that process, when the robotic link is somewhat here, it is off. So there is an advancement of the robotic point from the stop point. So there is a positive, there is some error. So there is an error, if the stop point minus the new position, that will be negative. So there is a negative error in that sense. So basically, this is called a steady state offset. So the steady state offset is a problem whenever, we stop the robot at the target point. We have to basically control the motion of the robot so that it can stop rightly at the stop point at some time point, slightly greater than this experiment. But that is possible that the robot can be stopping at the right point where you desire. Now, this is the same experiment. The two signals, motor imagery and error-related potential, these two signals are generated by this person. The link is again moved from the left, from the start point to the target position, as you find. Okay, using motor imagery and ERRP signal, you can control this thing as I discussed before. So what we do basically, when the person thinks of moving his right hand, he will be liberating motor imagery signal that can be preprocessed, and the preprocessed signal is then certain features are extracted from preprocessed signal, and those features are fed to a classifier. The classifier will say whether the person thinks of moving his right hand or left hand or nothing. If it is moving the right hand, then actually you have to generate a control command to move that particular right, to move that link, say, clockwise. If you think of moving your left hand, then the robotic link has to move, say, counterclockwise. So based on the classifier output, it is a clockwise movement required or counterclockwise movement required or no movement required. We can control the robotic link or the motor accordingly. So this is the motor which can be fired into clockwise or counterclockwise as decided. After the robot started moving, the subject is observing. So he is observing here. When it attempts to cross the target point, red mark stop point, the person will liberate the ERRP signal, error-related potential signal. So then that is feature extracted and classified into error occurs or error did not occur. If error occurs, that has only single meaning that the robotic link has crossed the target point. The pointer has crossed the target point, so an ERRP signal occurs. So in that case, the motivation is to turn the robot back from this point to somewhat here. You need to make the robot back, and that is done that is automatically done by the system. So effectively, on the motor, we are doing three things. First, motor imagery processing, then feature extraction and classification, and then control first time. And when he observed the error-related potential, again he pre-process and feature extract and classify that thing that ERRP occurs. And in case ERRP occurs, we stop the motor and turn it back by some angle. Because if the motor is here, motor is somewhat here, it has to turn back in the opposite direction so as to align it with the red line. So motor first moves forward, then it crosses target point. It is identified, it has crossed the target point. It is turning back. So it is turning back means opposite direction. It is moving from here to here at the red line, and effectively you then stop the motor. So the steady state error in this case will be 0. Basically, the program is very simple. You just check whether motor imagery is detected in the program. If motor imagery appears, then what to do? That means person thought of moving his hand, so start the motor. If motor imagery did not appear, that means person did not move his hand, so wait in a loop when the person thinks of moving his hand. And when the person really moved his hand or thought of moving the hand, then motor imagery will be detected. Then we just command the motor to start. As the motor started, at one time point, it will cross the target point. As it crosses the target point, ERRP will occur. So we look for ERRP to be detected. If ERRP detected, then what happens? If yes, then error occurred. So we turn the motor back by a fixed offset and stop. If no ERRP, then we continue looping through. So this is the idea how it works. Before to do this thing, we need to make the subject, we need to arrange some training for the subject. If you do it on the first day, you won't be able to do. So this is the training time window. The training window are generated using 4 PowerPoint slides. The first one is on fixation cross, where the subject is asked to the PowerPoint slide for 2 seconds. He is constantly watching the PowerPoint slide to keep his brain free. Second is right hand motor imagination. The person is given a command to move his right hand for 3 seconds. So in that case, when the person thinks of moving his right hand by observing the screen, he is waiting. In the screen, actually, one motor will move by program, and when the motor crosses the target point, the person will generate the ERRP. So person is waiting to see the robot arm to cross the target position on a software video, and then he will be liberating ERRP signal after 2 seconds. So this is a training process where the person has to perform the training process over approximately 10 days for 2 hours a day. So 20 hours altogether experiment. So this is for one-dimensional control, it is very fine. But when you move for two-dimensional control, it becomes more difficult. For example, suppose there is a ball on a stand. There is a ball on a stand. And this is a robot arm, OARB. OARB is the robot arm. This is link number 1 of the robot, then link 2, and this is link 3 of the robot. These are called joints. These are joint 0, joint 1, joint 2, joint 3, and so on. So joints are defined in the manner as humans have joints like, say, shoulders, then elbow, then wrist. So for robots also, they have joints like this. And these individual arm of the human, say forearm, are like this. So they are called basically links for a robot. So the robotic links are OARS. They are the robotic links. The ball is placed on a particular, say, stand. The motivation here is to bring the ball from, suppose ball, this is a line RB, but the robot is lying on the plane OWQ, but the link RS is below the ball. As the link RS is below the ball, the subject thinks of moving his right hand. As the subject thinks of moving his right hand, he is liberating motor imagery signal from the left side of his motor cortex, that is C3 electrode, and that signal is processed, and the computer understands that the person actually thinks of moving his right hand. So it commands the robot now to move the link RS up so that it can grip the ball. So the link RS, which was down the line RB, now moves up, and now it is in the position of B. But it cannot stop there. It will move past the ball. As the link RS crosses the ball RB at one point of time, the person observes what is going to happen right now. The link RS now goes to cross the target position RB. And once he observes this, immediately will releasing the error-related potential signal from the midline of his brain, the ERRP signal. And using that, detecting the ERRP signal, and it will be commanding with the BCI system will command the robot to stop. But by that time, the link RS is somewhat here. It will stop there. And then it is turned back by a fixed offset angle. So fixed offset angle is SRB, The angle is actually obtained by 100 trials or previous 100 trials, experimental trials, and taking the average value of the offset angle, and then giving a command to the robot to turn back by the fixed offset angle, so that RS actually gets aligned with the line RB. So this is the protocol we followed when the robotic link moves on a plane. So we have experimented when the robotic link moves along an axis and the target is a point on a line, on a particular curve. In this case, the target is a line. Target is a line on the plane. The line is in this case RB on the plane OQW. But target could be itself a plane. For example, suppose the ball is placed on a stick, something like this, and it is in the plane OQW, and the entire robotic arm OARS is in the plane OPW. So in this case, the robot is placed in the plane OPW and ball is in a different plane. So the entire robot arm now needs to turn counterclockwise. If you see, put a watch on top, that means watch is here, the watch is moving clockwise. So entire plane OPW containing the robotic arm OARS now needs to be turned clockwise. But how will you turn it clockwise? The subject simply thinks of moving his right hand. As he thinks of moving his right hand, he will liberating the motor imagery signal from the left part of his motor cortex. And then that signal is detected, and that is used to command the robot to start moving around axis OA. So it is moving from plane OPW towards plane OQW. But a point will come when the robotic plane or robotic arm OARS lying in the plane OPW will ultimately cross the plane OQW and move somewhat here. As it crosses the target plane, the person observing this will release the ERRP signal from the midline of his brain, because the robotic plane or the robot arm is now going to cross the target plane of the ball. So the person will liberate the ERRP signal when OPW crosses OQW by turning along this axis. And once the person observes OPW to cross OQW, he releases ERRP signal that is detected and then by the BCI system. And again, that signal is used to command the robot arm to turn back from OPW, here OPW, to OQW by certain angle. This certain angle, how much angle, that is determined from previous experiments, 100 experimental trials for the same subject. That means you do similar experiment 100 times, compute the average value of the angle, and then give the command to the robot arm to move from OPW somewhat here to OQW by turning by that much angle. And by that way, the robotic arm will be in the plane like this. But in this case, since the link RB and RS may not be aligned, we need to move up the link further, and by the same process as we discussed in the previous slide. So what we found here, in this case, the target is a plane, and when the target is a line, means RB is the line on the same plane. So we need to again move the robotic arm from this situation after the robotic plane OPW, which was outside the plane OQW, now turns back by a fixed offset and aligned with the plane OPW. The situation may be something like this. The robotic arm OARS is lying on the plane OQW, and then RS needs to move up again by one motor imagination, and when RS crosses RB, the subject will release one ERRP potential signal, error-related potential signal, and by that the robotic link, which was here, will be turning back towards RB and stop. So how much is the offset angle? That is again determined from previous 100 experimental trials. So this is the idea how you can control a robot arm in 2D plane in this case, in 3D plane in this case, and over one-dimensional case in the previous example. This is the one-dimensional case. So that in general is how did we use for the control task. Now here are the complete signals. So this is a subject, for example, and we use certain channels like F4, F3, C4, C3, P4, P3, and we extracted certain features from those signals to get motor imagery signal. Then there are 3 links for the robot, as you see. For this robot, this is link 1, this is link 2, an entire thing which actually has 3 links, but we just use it as single link because the remaining 2 links, these 2 links, we do not trigger. We just use link 1 for this, link 2 and link 3, and that too in a fixed order. Whenever we develop this part, in one presentation, this was done by Swagat Bhattacharya, who is also your presenter right now. I do not know whether he is presenting this, but he is a speaker in this forum, and he actually did his PhD program under my guidance, and another professor who expired recently, I mean, he is also from Jadavpur University. So basically, he is now in Ireland, and he did work on his PhD on this particular problem. So this is also published in a IEEE transaction. I also asked Boishali to send this paper also, Swagat's paper. So basically, what Swagat did, he comments the robotic link 1, 2, and 3 to trigger in fixed order, because at that time we did not know how to communicate the robot which link to trigger. So first we tried with link 1, then if the error is not 0, we tried with link 2 and then link 3 in the fixed order. But suppose we do not always require to use all the three links. When the object is very close to you, you may only require only one link. But at that time, we did not know how to communicate to the robot by BCI, means brain computer interface, means which link to trigger right now. So we had a time delayed system. First we communicated link 1, then with some delay link 2, then with some delay link 3, and the process was done in that manner. So there are three link dynamics, and the feature extracted that ultimately sent to the link classifiers. These are link classifiers having three class outputs: clockwise movement of the link 1, counterclockwise movement of link 1, or no movement of link 1. So when this is triggered, this path is triggered, other two switches are off. So link 1 can be only link 1 classifier will be triggered to classify any one of these three outputs. And suppose if it is giving clockwise, then the motor driver logic comments the robot arm, comments the link 1 of robot arm to drive clockwise, and the robotic arm will move clockwise. In the same manner, after some delay, link 2 will be triggered. It may be needed to move counterclockwise, and then after some time, link 3 may be triggered, which may be required to move clockwise or counterclockwise as decided by the control logic. Once the robotic link moves some angular shift, then effectively you can find there may be error, as we found here. There may be error because OPW plane crosses OQW, so there will be error. And under this circumstance, the ERRP signal will be released by the brain, and it is collected at FZ, CZ, PZ electrodes. Some features are extracted and fed to a classifier to check whether error condition occurred or did not occur. If error condition occurred, the robotic arm, which already started moving and crossing the target point, now is commanded to stop and move by a fixed offset. So this is done by a separate parallel channel for error feature selection and error classification to command the robot to stop. So by the two process, one is a motor imagery signal and ERRP signal, we could control the movement of the robot arm as desired. Now I show two videos to demonstrate this. This is one video where there is a ball and there is a box. The person will think of just moving his left hand or right hand, left hand to trigger one robotic motor clockwise and right hand to trigger any robotic motor counterclockwise. These are EEG electrodes placed on the scalp of the subject. They look like metal buttons. These are two reference electrodes are placed at the two ears. The signals are captured from the brain and is going to the EEG system. This is the EEG system where there are EEG amplifier and AD converter, analog to digital converter. The converted signal is connected to a computer to generate the control command for the robot. So there are two computers, one is connected with the EEG machine and another computer connected to the robot arm. And the computer to computer communication is done by wired means. These are the brain signals acquired by the EEG collecting device. The electrodes are shown here. Corresponding channel signals are activated as you find. Now the operation starts. The person will think of moving this link towards the plane of the ball by thinking right hand movement. She's just thinking right hand movement, it moved. But it crossed the target plane, so found error, and she commanded the robot arm to turn back. She commanded the robot arm to reach actually this link by link 2. And now she wanted to make the gripper horizontal. Unfortunately, it is not horizontal, so she again corrects it by error-related potential. Now she wants to move her right hand twice, that means gripping. Now she wants to move her left hand twice, which means to move this robot arm by 45 degree, but it has more than 45 degree. So error occurred. She wanted to bring it down. Now she wants the robotic link 1 to move towards the plane of the box. It moved, but there was error corrected. Now he wants to bring this link down, but it is going out to the plane of the box. So there is an error, it is corrected. Now she thinks of moving his left hand twice, which means releasing the block, releasing the ball. So the ball is released. In this manner, the robotic arm, which is an assistive device, can be controlled by the person's thoughts only. Now I show you another video. Can you see the video? Hello, professors,
Yes,
can
sir.
you see
Yes.
the video?
Yes, sir.
Okay,
Yes, sir.
okay. Now I show you the second video. Now, whenever we develop this in Swagat's paper, the reviewer said, if you have more number of links, it will not work fine. And their idea was correct. Up to 3 links, it is giving very good result. When you increase the number of links, then the motion, then effectively results are poor, because when the robot makes a small error, it cannot be corrected online. Just see the video for 4 links. So same robot configured in a different fashion. This is another student. I mean, she did her PhD from ISI and did her master's with us at Jadavpur University. She is Nehalika. The previous student was Reshma. She is now a professor of USA. So this is the brain. You can see the brain activation by colored patch from the back side. Here also the person needs to pick up the ball by the robotic arm and transfer to the box. But she uses 4 links. 1, 2, this 3, and here 4. See, there is an error. As error occurred, correction will be difficult in later stage. She has to plan which link to fire. That is done by, some LEDs mounted here on each link. I will discuss this thing later, how link can be triggered separately. So person is simply thinking to move her right hand or left hand, and whenever she finds the robot to commit error, she will be liberating the ERRP signal. Using this motor imagery and ERRP signal, entire operation is carried out. See, it has moved far away from the box, but it has to go to the box because initial error was high, so the error is continued. That is the limitation when increase large number of link. It is trying to correct it later, but accumulated error is more. Now it will drop the ball, but still there is a high risk ball could go out, but fortunately it will be falling inside the box. So this is how actually it is done for 4 links. So you understand, when you increase the number of links, the result may not be so good. Up to 3 links, it is very good. So basically, we have the results. We did the experiments, we got very good accuracy of 91% by using, certain classifier, Basically, we are using actually for motor imagery classifier, we use, we basically use initially, say, singular value, we use support vector machine classifier, linear support vector machine classifier, and we got, 91.6% classification accuracy. You can try with other techniques that we did later to improve the classification accuracy. The computation time taken per control command is 0.282 seconds. The controller performance is also here, that is denoted by steady state error, peak overshoot, settling time. So settling time is large, 56 seconds here. We did experiment with different features for motor imagery as well as, say ERRP signals and different classifiers, and we got different training time and average classification accuracy. It is found if you use dot parameters and power spectral density, then, if you use SVM classifier, then motor imagery classification is good. Training time is 8 minutes and classification accuracy is 97.2%. That is the best one. Additional further improvement that we did in two subsequent papers after Swagat completed his paper, Arnob Roxin, another person, completed his work, and he is now in United Kingdom. He is doing postdoctoral research in United Kingdom. He is in Kolkata for a few days. So what he did automatic method for or link selection. Previously, it was a fixed order link selection in Swagat's method. Arnob did it automatic link selection by placing electrodes, just so in the next slide, somewhat here, by placing, I mean, say LEDs at different links, and the LEDs can actually blink with different frequencies, 8 hertz, 10 hertz, and 12 hertz. When it is blinking at 8 hertz and the subject wants to control this link, he will simply look at this link. So this will be liberating some steady state visual evoke potential from the brain, from the occipital lobe of the person. That means the 8 hertz signal, which is where the LED is flickering, that 8 hertz signal will be appearing from the occipital lobe of the subject. If the subject looks at this link and the LED is glowing with a frequency of 10 hertz, then he will be liberating 10 hertz signal. So the person simply has to look at the right link where at a particular LED is flickering, and that signal will be coming up from the brain, from the occipital lobe. Then by processing, the BCI system will come to learn to which link the subject want to address. That means which link the subject want to control. So this is the new achievement that that Arnob did after Swagat completed his PhD. And additional thing is, I mean, the steady state error he has decreased by allowing the link to move around the target point multiple times. Each time the link crosses the target point, the speed is reduced to half to its previous speed. Suppose initially, first time when the target is crossed by the robot arm, the speed was high. As it crossed the target, the speed is reduced to half value, and then and the robot is commanded to turn back. As it is turning back and again cross the target position, the speed is reduced to half and it is moved forward. In that way, each time the robotic link crosses the target plane here, as you find, each time the robotic link OPW crosses the target plane OQW, the speed will be half, and in that way, gradually, speed will be reduced, and the robotic link OPW will be aligned exactly to OQW, with steady state error being zero. That is the advantage. So Arnav has done two interesting things. One is the reduction in steady state error, and other is selection of individual link whenever which one is required. This is published in a very well cited work in IEEE transaction. I will also ask our PhD scholar Vaishali to send you this paper too. You send them to actually to Anuradha ma'am, yes. Now, Vaishali, who is assisting me and sitting beside me, is doing some interesting work. What she is doing actually, she identified, that the fundamental problem that appears in the previous two works is to engage the person all the time during the control process. The person has to pay his attention throughout the control process. But is it possible to make the person make less attentive throughout the control process? Is it not possible that the person can only identify the target thing he wanted to get towards his mouth during a dinner table or during say breakfast? So in the breakfast table, there are a number of say fruit juice on the table, and this person suppose wants the orange juice, which is here, instead of others. So person will simply look at the orange juice, and the robot arm can automatically reach there. How is it possible? Boisali says it is possible to break the problem into two halves. In the first half, you have to identify the XYZ coordinate of the glass the person wants to sip. If the person wants to sip the orange juice, then the XYZ coordinate of the orange juice has to be identified. And the person may be left free. The rest of the control task of the robot to reach there and to bring it towards the mouth of the subject is an open problem that can be done by traditional multi-loop controller. So just the task of the person is to make the robotic system understand the coordinate, XYZ coordinate of the target point where the robotic link has to reach. That is the first strategy. And in that case, the cognitive load of the subject, which was heavier earlier because the subject has to be attentive throughout the control process, now is reduced significantly. So what is done here, how the person will identify the XYZ coordinate? Boisali says, and she did some work, that there are three light sources, one red, one green, and one blue light sources. The green and red light sources, they are flickering at different frequencies. They are light emitting diode based light sources. This is flickering at 8 Hz and the green is flickering at 10 Hz. And there is a blue light pad that is around the entire table. That is not flickering, that is a fixed blue colored light that will simply move up. In the first case, the X light beam, the red light beam, which is X light beam, moves over the glasses, and the person is watching the orange glass. When the flickering red light beam crosses the target position, that means the glass, the person will actually being a person being attentive to the glass will find some flickering signal here. And on getting the flickering signal of 8 Hz, he will be liberating the 8 Hz signal from his occipital lobe by the signal, by this EEG signaling process called steady state visual evoked potential. That means as he finds the flickering signal to fall on the glass, he will be liberating the steady state visual evoked potential of 8 Hz, that is the flickering frequency from the occipital lobe. The BCI system will accept that thing and comes to learn that the 8 Hz signal appears because the red light beam which was flickering us at 8 Hz just is on the top of the glass at that point. So, but how many steps that this particular red colored flickering beam has moved? That is being controlled by a separate stepper motor controller, and the stepper motor driver is used to move this red light. So effectively, how many steps the motor has moved, that is counted to come over here, and then the x coordinate of the position of the orange glass is identified. Similarly, the another flickering beam of green colored of say of green colored, stop হয়ে গেছে নাকি? Another flickering beam of green colored at 10 Hz is moving towards the y-axis over the plane, and the subject is observing at the orange colored juice. Once the flickering light beam falls over this, the subject will be attentive that a flickering signal of 10 Hz appears on the orange juice, and he will be liberating the 10 Hz signal from the occipital lobe, the steady state visual evoked potential. This signal is then identified by the BCI system and then commands the robot arm that the XY coordinate is now identified. And then the Z coordinate needs to be identified. For getting the Z coordinate, the entire, the the blue colored pad, as you find, which is not non-flickering, a fixed light beam colored pad, which is around the table, now gradually moves up from the bottom of the table, from this plane of the table, gradually moves up on the top up to the top of the glass. The person is observing and he needs to identify when the blue light attempts to cross the top of the glass. When it attempts to cross the top of the glass, the person identifies that error is being committed by the blue light and immediately will be releasing the error-related potential signal anywhere from the midline of his brain. Best signal will be obtained from PZ electrode here. And this is by error-related potential signal I discussed earlier. So X and Y coordinate, which are determined by steady state visual evoked potential, and here error-related potential signal or P300 signal. When it crosses the target point, a P300 signal, a large peak power from parietal lobe is also obtained from 300 milliseconds from the onset of the subject's observation of this light pad crossing the target point. That means when the person observes this light pad crossing the top of the glass, after 300 milliseconds later, the person will liberate another signal from parietal lobe, either using error-related potential signal or by P300 signal. Either of these, the coordinate, Z coordinate of the glass can be identified. Then the computing system computed Z by 3, and the gripper will hold the robot arm at X, Y, Z by 3 position. So the robot is now programmed previously that from his current home position, it will come to this particular position without hitting any obstacle. That way the program is developed. So it will come to the gripper will come to the position of the X, Y, Z by 3 of the robot and hold up here. And the robot is then programmed to bring this glass towards the mouth of the subject who is sitting very close to the table. And again, without hitting any obstacle. How does it move without hitting any obstacle? For that thing, we are using basically two things. One is inverse kinematics and obstacle avoidance program that we are using together to actually move the robot arm from one position to another. And by two steps of movement, one from the home position of the robot to the glass And then from the position of the glass to the robot subject's mouth, the two-step path planning program is used to bring the glass, towards the mouth of the subject to allow the subject to sip the orange juice. So this is the idea that actually Boishali has developed. In the first steps, he developed the coordinate and how the control is done. Yes, once the XYZ/3 coordinate is identified, stop হয়ে গেছে বোধহয়. Once XYZ/3 coordinate is
No, sir,
identified,
it's moving, sir.
it's moving. Okay, then the control policy is used something like this. This is the host computer which knows the XYZ coordinate. It submits the XYZ coordinate to the robot computer. Then the robot computer determines the inverse kinematics from the home position of the robot to the target position of the glass to move. What are the link angle changes? The link angle changes from link 1 is theta r, for this link is theta phi r, and for this link is psi r. So theta r, phi r, psi r are the angle movements required from the home position of the gripper to the glass position, and they are controlled by a local controller. So local controller actually is getting feedback from potentiometric feedback from the 3 robotic arm, and these are the feedback signals. So the error signal is obtained, and error signal is processed, and based on the error, the control command is generated to the motor driver logic. So they are the control command from the motor driver logic that is generated by 3 local controller for 3 links of the robot arm. The motor driver then actually commands the robot to move by the desired angle, and whether the desired angle is crossed or no, that is being managed by local controller. So the whole process is a hierarchical control system. These are done by DC motors, 3 DC motors for local controller management, and the robot computer actually generates by inverse kinematics the angular movements required for the 3 links. The motor driver simply commands the control signal to the robot arm for the movement of the robot by the motors. So motor is inside here and local controllers are outside. Motors are actually provided by the manufacturer, the robot, and the controllers actually we developed ourselves in the lab. Now it details the control algorithm. In this work, no, actually, your coordinator Anuradha ma'am is also engaged. Boishali ma'am, actually, who is my assistant here right now, is being supervised by Anuradha ma'am and myself in her PhD thesis. She has joined for 1 year, and during this time, she has developed the control loop and stability. She uses here a fuzzy control, but a different type of fuzzy control. The one I discussed, but I did not name, that is called Mamdani type fuzzy control. But here he used Takaji Sugeno type fuzzy control, which is more sophisticated. Because of time, I could not discuss Takaji Sugeno type fuzzy control. Here she is using error and error derivative. There are 2 loops as you find. One is the position loop outside, and other is the inner loop that is controlling speed of the robot. So the position loop actually for individual link of the robot arm, say for theta r link, as you find. For theta r link is the first link for local controller 1. So similar 2 loop system is there for the other 2 angles. So for theta r link for one link 1, what is done? This is a Takaji Sugeno controller that determines the armature voltage of the robot, which is in turn of in response to our actual torque of the robot. But there is a torque variation because the robotic arm may pick up any glass. So when the big glass is there, torque is different. Small glass is there, torque is different. And because of the torque variation, you need to understand when the pickup is done, how much torque has to be generated. So the robot speed and armature voltage are to be adjusted. That is done by Takaji Sugeno fuzzy controller. And then after the armature voltage or the torque is produced, the inner loop is actually controlling by a tacho feedback the speed of the robot arm. So outer loop is outer loop is position control loop, inner is speed control loop. And finally, you are ultimately able to control the position. The Takaji Sugeno controller works in the manner. If error is something, say medium, and derivative is rate of change of error is small, then armature voltage is a linear function of K1 into error plus L1 into derivative. This K1, L1 or K2, L2, they are Takaji controller parameter, which Boishali ma'am has developed by using a separate learning controller, separate unit that is called a learning automaton. So by using the learning automaton, automatically she will be developing the value, determining the value of K1, L1, K2, L2 for different rules, for different torques of the motor. So during experimental setups, you will pick up different glasses with complete filled up fruit juice or partial fruit juice, and then can automatically generate the right torque by experimentally setting K1, L1, K2, L2 using a special time of learning automaton which is connected with the Takaji Shugeno controller. And after that, she did the stability analysis of this thing by Lyapunov method and also by root locus technique. And she found that the system is stable when certain parameter like K and L satisfies this range 0 to 19 for K, and for L must be greater than K, that means greater than something, but if K is say 5, the L must be greater than 5 and less than 11.1134. Now let us conclude the session. So in this session, we developed one method for translating human thoughts into action by artificial means, and that is a very challenging work. It provides an opportunity to develop any kind of position control scheme by your thoughts. EEG is a very interesting device for real-time control for brain signals because you can get the signals in real time, unlike MRI and other signals where you don't get the signal in real time. EEG is very cheap and but provides very important time valued signal. So you can easily use those signal for any BCI experiments wherever you require a very good temporal response. But EEG is poor in spatial response. If you want to identify what the brain is doing over time, then EEG is not so good. In that case, you can use fMRI, functional magnetic resonance imaging, or its low version, functional near infrared spectroscopy, where infrared imaging is used, which is relatively low cost device. Now, motor imagery and error-related potential signals are used for position control of the robot arm. This is new. ERRP-based position control has not been done much earlier when Swagat started the work. But now most of the people used MI and ERRP or MI and P300, these two signals to control position control for robot arm. Previously, we did with fixed order position control where you needed to control first link 1, then link 2, then link 3 in fixed order because you did not know which link to communicate. But later on in Ordnov's research, we could communicate the link by BCI means by connecting an LED with proper frequency. And the LED is flickering at a frequency, and when the subject is observing that link, that particular frequency of light appears in the occipital lobe, and the BCI system comes to learn that the subject is observing that link. That means subject wants to do something with that link. So automatically which link needs to be controlled is actually communicated to the robot by BCI means later on after Ornov's work. So random order link selection can be done rather than fixed order link selection. To improve positional accuracy, that means less overshoot and undershoot, I mean, what we did, we use multi-loop control, as actually Boishali ma'am has done multi-loop control that gives very good accuracy, where outer loop was for position, inner loop for loops for speed. For example, suppose you are driving your car on the bypass. So you found, a dog is moving here and there, just attempts to cross the road many times, but could not cross because the dog is actually pregnant. So basically, you understand the dog is pregnant and he's heavier. It is afraid to cross the road, but it is thinking to cross the road because car is far away. So it moves many times to and fro. It has a to and fro motion. By noticing this, what you could do, you have to control the speed first, and then you can control the position. If you try to control the position to stop your car before the dog, you won't be able to do that because you will be actually cross over the dog. But if you need to control the speed, in an inner loop, then control the position, you have a better chance. And the same thing has done by Boishali ma'am to control the position by controlling the speed in an inner loop, so stability will be better. And she has provided one method to decouple the problem of identifying the position of the target and controlling separately. Unlike, the other two people that Swagat sir and Ornov sir has done, what they have done to basically to control the entire robot arm, and throughout the process the person has to be attentive to do the control task. But Vaishali ma'am has done something where the control task will be done deferred by automatic means, and the identifying the target position is done by the BCI means. So that's new. So this is all about the presentation and topic. And now here are some interesting, publications. The first one by Anuradha ma'am, who is your coordinator. She did for driving, but this is useful. And many other papers, most of them published in IEEE transactions. Okay. And you can see Annesh MM also is a speaker to you. See, published Swagat said is also a speaker, and he worked with myself and Professor Tewariwala, who expired during Corona. Then this is Swagat's another paper. Then this is another by Lydia Ghosh, who is now a professor of RCC College, Kolkata. Okay, she got positions, postdoctoral positions in University of Rutgers, but during Corona she could not move. And you know, this is again another paper by Arnav sir, which is very important paper. Vaishali ma'am will send you. That I discussed also. And there is another work by Mousumi ma'am, who was our ex-student and now is in, say, IEM College, Kolkata in AI department. So that's all. Thank you for a patient hearing. If you have questions, please ask me now. We keep some time for question and answer session. Question and answer. Anybody goes to come out? Yes. So if you have questions, please ask me.
I would like to ask our dear participants that if anybody has any queries, please feel free to ask Sir. Sir will
Hello.
be delighted to answer you. Yes, yes. Yes, sir.
Sir, in the
Good
last
evening, sir.
example,
Yes. Yes. Ask your question.
Good evening, sir.
Yes. Yes. Please ask your
I
question.
want, yes, yes. Sir, my question is for the upcoming PhD topic in this area is please suggest me. This
Yes,
is the
there are.
combination of all video analysis and all kinds of image also.
The first topic, that is on emotion part, it was on video
Yes.
analysis and image
Huh.
analysis part. Okay, in the first
Okay.
presentation. The second
Yes.
presentation does not have much with video and image, but it is on brain signal analysis and classification problem. Okay, both
Yes.
the topics can be taken up for PhD problem, and there are active PhD research works going on in the world on both the topics.
Okay. And sir, how data can be real, can be collected that regarding that data set?
Okay, for data set, no, I mean, you can collect the data directly from the machines. For the first case, you can have a face data. We have some face data that we developed ourselves when Anisha, one of our another student who is not a speaker, but she actually developed some work for, say, interval type 2 fuzzy set based emotion recognition, which I discussed. Anisha is now a professor of Institute of Radio Physics and Electronics, Kolkata University. So basically, in the data she prepared, and there are some standard data sets available for face emotion recognition. You can get the data, from many data sites. One is Japanese data, one is say Konar data. There are many interesting data set both for black and white and colored images. So data are available, and some of them are free.
Okay. Sir, I am prepared just on this topic, but in future I want any query in this, then I
You
will
can ask me
definitely
by
talk to
email.
you.
You can ask me by
Yeah,
email.
okay, sir. Please give
Uh,
your email.
uh.
Definitely I will call back you.
So that is Anuradha ma'am. I think will be submitting my email. I can tell you now, konaramit@yahoo.co.in. But if you forget, ask ma'am.
Dear participants, I am just writing the sir's email in the chat box. Please follow.
Okay, sir. Thank you.
konaramit@yahoo.co.in. এই chat box টা দেখতে
hello.
পাচ্ছি। Yes, please ask.
In the first example, sir, as you show, and actually, I also know when I was your student that if a user moves the hand of think only just movement of his hand, then only the robotic arm will move. But in the last example, you show that the user only thinks about the LED. That means the light. That means it depends on RGB or something red
Not,
color
not,
or
not
green color.
RGB. Basically, in the second case, I mean, when this is called SSVP signal, steady state visual evoked potential, which I did not discuss, was in the slide, but I did not discuss. The idea is whenever a person see any flickering signal, okay, a person observes a flickering signal. Flickering means it is say changing, frequency changing, say light is on and off kind of signal. Then that signal is picked up by the brain. And then from the occipital lobe, that signal frequency will come out. So from that signal frequency, the BCI machine can understand, the program can understand the person is observing some flickering signal that is actually an LED connected here on the arm of a robot. So the person actually wants to communicate with the robotic link. That was the thing.
In
That's a
that case,
different signal.
in that case, why it is necessary to different frequency LEDs?
Because for three different arms of a robot, for three different links of a robot, how will you distinguish them? When the person wants to communicate with link 1, the frequency is suppose 8 Hz. For link 2, it is 10 Hz. For link 3, 12 Hz. So when the 12 Hz signal comes out from the brain, the BCI machine will understand, program will understand the person wants to communicate link 3, not link 1 or 2.
Okay, sir.
Okay. Any other question? If any of you have any other question, you may please ask.
Dear participants, if you have any questions, please ask. All right then. So, sir, we are actually wrapping up then today's this enlightening session. So it is my great privilege to extend our deepest gratitude to our esteemed resource person, my supervisor, my mentor, Professor Amit Konar, for his invaluable contribution to this FDP on innovative pedagogy with AI and ML, exploring intelligent model predictive control. So actually, sir, session on emotion recognition and control using classical and type 2 fuzzy logic and brain-computer interface in neuro-motor rehabilitative robotics were not only informative, but I must say it is also highly engaging. His expertise in these cutting-edge areas has provided us with profound insights that will surely enhance our understanding and practices in this field. So on behalf of Netaji Subhash Engineering College and the Department of Applied Electronics and Instrumentation Engineering, I sincerely thank Professor Konar for his time, dedication, and willingness to share his knowledge with us. We are truly inspired by your work, sir, and grateful for the opportunity to learn from you. So we look forward to future collaborations and hope to have you with us again soon. So thank you so much, sir, for this wonderful experience.
So thank you, Anuradha. I should not, what should I say? I do not know, gratitude or whatever you call it. So we are really very thankful to all the audience and the organizer, Anuradha and Pratusha. They are my favorite students, but now they are quite senior, but still they are my favorite students, all-time students. And, so I like, I was very happy to be present, among so many people here. And if you learn little bit or if you have any questions further, I'll be happy to share my knowledge with you. So you may ask anytime any questions over emails. Okay. So ma'am has already shared my email in the chat box. So if you have any questions anytime, you can ask me. So that's all. I think you can complete the session now. Because
Okay,
if
thank
there
you,
are no
sir.
questions, yes.
Yes, sir. Thank you, sir. I just want to take 2 or 3 minutes from
Okay.
you, and I will try to, contact all the participants. So, and I request all of you to just turn on your camera so that I can take the attendance for this session, which is a very mandatory to upload in ATAL FDP portal as well. So, please, participants, just turn on your camera for 2 to 3 minutes.
So thank you all. Okay.
Thank you, sir.
Thank you so much.
Many
Thank you so
familiar
much.
faces, sir.
Yes, many familiar faces. Yes. Bye.
Bye, sir.
Hmm.
Okay, so thank you so much, participants. It is a wonderful, wonderful experience tonight, and I wish you all the good nights. And we will again meet you tomorrow at 6 p.m. sharp. Thank you so much.
Thank you.
Thank you,
Bye.
sir.
Bye.
Thank
Thank
you,
you,
Okay.
sir.
sir.
Okay.
Bye,
Okay.
sir.
Bye. Bye.
Thank you, sir. Bye.
Okay. Thank you, Anuradha.
Thank you so much,
Right.
sir. Sir, I will connect you. Thank you so much, dear participants. So I am just closing the session
Closing. Yes.
and meet you tomorrow. Okay.